So to be able to work on inductive argument effectively, you need two things. First, of course, is that you must be able to determine a very relevant results to be used for proving each and every term, as you do the work. And the second thing is that you show that to prove each term, it depends on the previous term, and these two things are important. You find relevant results that could be used to do the proving, and they show that to prove each term really depends on the previous term. So with these two things in mind, you can now proceed to look at the examples, the next one. So let's start by reading this through this question carefully. Right now you should perhaps stop the video for a while and think about this and write down a strategy before you proceed. Now if you look carefully, it's way easier to come from the right hand side to the left hand side, and we're going to start by letting n equals to 1 in this expression and show that it's going to be equivalent to 1 plus this theta. Right, so as you can see that when n is 1, the right hand side of the expression gives you this one, so it becomes n plus 1, so therefore it's 2 theta. And I know about polar forms that SACE 2 theta is actually equivalent to SACE theta times SACE theta. Well, in other words, this means that this is really 1 minus SACE theta of square, and this is 1 minus SACE theta. If you look at it carefully, this whole expression, especially the one at the top, you notice this is equivalent to 1 minus u squared. So what I could do is then factorize this as SACE theta, and it's the sum SACE theta, and so you could see clearly that I could then eliminate the common factor, and I'm left with 1 plus SACE theta, which exactly proven that this is 1 plus SACE theta when n equals to 1. So now that the result is established, it's being true when n equals to 1, I could now move on to n equals to 2. But since I have shown that the result is true for n 1 plus SACE theta, I would now try to return to the left hand side and try to work from left hand side, and the first three terms, the sum of 1 plus SACE theta plus 2 times SACE theta, I'm trying to show that it's going to be equivalent to 1 minus SACE 3 theta over 1 minus SACE theta, if you think about it. Alright, okay, so we're going to start from by starting with from this 3, and I'm going to show that it's equivalent to this one where n equals to 2. We have established in fact earlier that this result is true when n equals to 1, so we could proceed to use this in here as follows. So you can clearly see that 1 plus SACE theta is actually here, this result, and we just replace it. And of course, now we're trying to simplify this. You could clearly see that we are getting close very soon, getting very close to our what we need to show. We know what we're going to get in the end. Right, we know that eventually we should see this, where this is the result of this by replacing n equals to 2, and then you should end with this. So let's continue on with the work here. Well, okay, I think I made a mistake here, and it should be 1 minus SACE theta, and the outcome of this will be 1 minus SACE theta as the denominator. This is still SACE 2 theta. When you expand this, this like magic. Yes, it look really good, and you could see that this term is going to cancel out this term, and whereas this term is really SACE, the product of two polar form is the sum of the arguments So this really is a SIS3 data, and you got what you need for n equals to 2. So if you be careful about this, think carefully, but you will notice that this part, the step 2 and 3, are really that common method, that common results that you're going to continue using, repeatedly use to show the next term and next term. And I'm going to demonstrate that in the next term, proving of the next term. So alright, this here the 3, now the sum of the first 3 terms plus 1, and the first 3 terms I've already proven earlier as being this 1 minus 6 3 theta over 1 minus 6 theta and plus this 3 theta. So you can see that we are using these results we've proven earlier, and then to try to prove this the next term, which is the one right now. So let's continue on, moving on and see what we get. So this is what you will get. You probably see by now that if you expand this, the numerator, you end up with seeing 6 3 data plus 6 3 data and minus 6 3 data 6 data, and we know what this last term is. This is really the 6 4 data, and the others we could cancel out, and so finally you end up seeing 6 4 data over 1 minus 6 data, which is exactly what you want to prove, as you can see here. And so now it's time to write down the conclusion. So looking back, we show that we could prove that the formula is true when n equals to 1, and also we could use the previous results to prove the next results, and we will conclude by saying that by inductive argument, actually you should start off by saying that as the formula is true for n equals to 1 2 3. So you didn't prove the fourth one, but it doesn't matter. So because it's true for 1 2 3, and there's a way for you to actually prove the next one using the previous results. So you say that by inductive argument, the formula is true. It's true for all positive integer more larger than 1, of course, and 6 data can't be 1, or you see, okay, it can't be 1, because if that is the case, the right hand side of the formula formula would not be true, because the denominator is 1 minus 6 data, then it will be undefined. Will be undefined. So that's why we know that we could say that 6 data cannot be 1, and of course n must be greater than or equal to 1.